All right, 8:30. We're ready to roll. Hello, online people. Good to have you guys here. Today's Friday. The plan for today is to finish this unit, which is Unit 2. And we've already finished Unit 1, and you guys are aware your sapling homework on Unit 1 is going to be due Monday. And we have office hours. I have office hours immediately after class for half an hour and again after class on Monday. So you have 2 chances to see me in office hours before this is due. And it's due, I think I said last class, 11 a.m. I just checked, it's 11 p.m. So yeah, you have all day Monday and then you have to pass it in sometime in the evening. Otherwise, the reason we usually pick 11 or like 11:30 or something like that, and not midnight, it's 2 reasons. One, I guess we could say we're concerned about your well-being and we want you to get to bed early. But really, what I've noticed is people confuse 12 a.m. and 12 p.m. and they're not quite sure if 12 a.m. or 12 p.m. is midnight or middle of the day. But if you have 11 p.m., it's clear. Everyone understands that's at night. So, although I mixed it up on last week, so say what you want about that. One other, I guess, piece of information to let you know is next Friday's class has to be 100% online. And that's because it's a very interesting story. I'm on a TV show. So you guys might know the show Curse of Oak Island. So I don't know if you've watched it before. I've actually never watched it, but I'm actually on this season. I've been doing work with them since the summer. Yeah, I got a watt up there. So I'm actually going to be back on the island next week on Thursday and Friday. And so what I've worked out with them is I'm going to be there like all day Thursday, and I'm going to stay overnight in a hotel. It's only an hour drive, but still, stay overnight in a hotel on Thursday evening, get up Friday, teach this class remotely from the hotel room, which is why I can't be here in person. And then they want me like immediately there on the island right after. So I guess no office hours next Friday, but I can do them anytime. If you want to talk to me, just pick a day that's not Thursday or Friday next week, and we can make it work. It can be Saturday, it can be Sunday. That's fine too. So we'll make sure this all works out pretty well. And yeah, shouldn't be an issue there. Cool. Are people doing okay with sapling? I've got a few emails, and it's not like people don't understand it, or not even that they're not sure how to answer the questions. It's more some people are having like little technical glitches, like the screen size, like it's like cutting off part of it, things like this. And I went in myself with my computer and I messed around with some of the questions, and I'm not seeing any problems myself, but it doesn't mean that you guys aren't. If you are noticing any issues, please let me know, and we can try to figure it out. One thing that I found fixed problems like this last year. Last year we weren't using sapling, but we were using sort of a similar, we were using the one that we made ourselves for first year, although both that and sapling are based on Moodle, so they're the same sort of back end. And what I noticed is, how when you're in your browser, you can like zoom in and zoom out, and I think it's Command plus and Command minus on the shortcut. I found sometimes if something was off screen, you could like shrink it a little bit and it would come back on screen. So that's something to try. I don't know if that's going to fix the problem for everybody or anybody, but just wanted to let you know that that's a possibility that's out there. I see a question in the chat. When's the second assignment going to be posted? I'll see if we can get that posted today. Oh, it's already posted? Yeah. Oh, well, there's your answer. Second assignment's already up. I did check yesterday and it wasn't up, so Terry must have posted it between then and now. See a question over there. Where can you watch the show? Oh, when it comes on? I think it's on the History Channel. I don't have cable, so I don't know. Can you get an app? Like HBO, you can get an app and you can like buy a subscription. I don't know. Maybe you can buy episodes on YouTube. I don't know. Honestly, I don't know how to get it. Yeah.
I was just wondering what kind of, work they will want you for there.
Oh.
I noticed they have a lot of like geologists and stuff there, but never anything chemistry related.
Yeah, so the question there for people in the chat who probably didn't hear that is, for the show, what kind of work am I doing there? Why do they want a chemist and not a geologist who's usually on the show? And I can't give you too many details because I'm bound under a non-disclosure agreement. Hunting for treasure, but definitely using chemistry and chemical techniques to look for some things that they weren't able to look at before. And yeah, it's pretty cool. We found, I don't know, I can't say what we found or didn't find, but yeah.
Did you have to audition for this?
Audition? No, I didn't have to audition. It was actually really weird at first because they came into my lab and they turned the lab into like a movie set. And first of all, they had to like remove anything out of the lab that had a brand name showing. And then, so even things like boxes of like Kim wipes and stuff like that, like, no, you can't have that around. And there was like a bunch of camera people with different angles and different zooms and basically the show is unscripted. So it's like reality TV, but it's unscripted. So they just like said, okay, just chat. And so we chatted for like an hour. And at first I was like nervous because you're being filmed for like a big show. And very quickly it became just sort of routine and a conversation. And then at the end, they like did close-ups and wanted you to repeat like a bunch of statements that you said before. So it was weird. It was like 4 hours of just nonstop. It took kind of a long time. Any other questions? Yeah, I have no idea like how many episodes I might be on or anything like that. I just know I've been filmed a lot for this. Well, not really a lot. Like I've been down there 3 or 4 times. They've been up here once. So yeah, they've got some footage if they want to, how much they want to use. But I'll let you know if I don't know if I hear anything about it. I can keep you guys in the loop. Back to organic chemistry. The reason why we're all here, right? We're talking about functional groups. We were marching through sort of the important functional groups. The last ones we talked about were aldehydes and ketones. And remember these two guys, I keep saying guys when I talk about, I shouldn't say that. These two functional groups, I shouldn't be personalizing them. Some people get really upset. Some chemists get really upset when you like humanize a molecule or an atom. Like this atom wants to have a full octet or things like that. They're like, it doesn't want anything. It's anyway. I'm not going to be like that. An aldehyde has a carbonyl group. A carbonyl group has a carbon double bond oxygen and a hydrogen. Ketone has a carbonyl group with carbons on both sides, right? So that might be like CH3, CH3. Notice how that CH3 I wrote backwards, this second one here. Normally you write it in the direction, so the first atom you write should be the atom that's connected to that bond. So it's connected to the carbon, the bond goes to the carbon, so I've drawn the CH3. But this way, I've written it the other way around, because you want it bonded first to the carbon. You don't want CH3, although sometimes you see it like that too. The carbonyl group is very polar. It's very strong bond. It's short. It's got 2 atoms that have a big difference in electronegativity. So we have quite a dipole moment when you have a carbonyl group. And if you look at these 2 compounds, one butene and one propanol, that are similar in structure, except one is a carbon-carbon double bond, one has a carbon-oxygen double bond, you can see then that the difference in the dipole moment is huge, like almost 0.3 dbi for one butene, 2.5 for one propanol. So you can see there's such a huge difference in the dipole moments. And that leads to about a 50-degree or 55-degree difference in their boiling points. That's because this aldehyde has strong dipole-dipole intermolecular forces as a result of this polar bond, this polar carbonyl group. So what we often see then for ketones and aldehydes is they can act as hydrogen bond acceptors because there's oxygens with lone pairs. They're somewhat soluble in water. They have reasonably, like I'd say, medium boiling points. They're lower than something that would have, say, an OH, something that has a hydrogen bond donor that can hydrogen bond with itself, but it's much higher than something that's nonpolar of similar size. This is different ways on the bottom here of representing the fact that this is a polar bond. You can use sort of the delta's disappeared here, but it's delta plus, delta minus. You can use the dipole arrow, or sometimes you actually use these resonance forms. And these resonance forms probably feel bad and unnatural because that compound on the right, we have formal charges, we have a carbon without an octet. It kind of breaks all the rules of correctly drawing a Lewis structure that you would have learned hopefully last year, maybe in high school, but definitely in chapter 1 this time, if you have to refresh your memory. This isn't really a great representation. It's not the best Lewis structure, but it does give you an idea of how this might be polarized, where the positive and where the negative charge might be. All right, aldehydes and ketones. Other groups, 3 more that also contain carbonyl groups are carboxylic acids, esters, and amides. So carboxylic acids have a carbonyl group, as you see right here, with an OH attached. Carboxylic acids are all somewhat acidic. They're all weak acids. And that's because if they lose H plus from that OH, that anion is resonance stabilized. Right? Because if you take, let's say, acetic acid, carbonyl with an OH, if you lose H plus, you have an anion where you can share that negative charge over 2 oxygens. Spreading out charge stabilizes things. So that's a fairly stable anion, relatively speaking. That means this is going to be a fairly good acid. We'll lose that quite readily. So carboxylic acids, super common in biomolecules. Well, amino acids are all carboxylic acids. Every amino acid is what reacts to make proteins in our body. Acetic acid we see here. Aspirin, you can see there's another carboxylic acid group in red right there. Ibuprofen, these are very common in medicine as well. 2 examples right here, but thousands of other ones if I was to go on and on. The pKa of these guys is around 5, usually. Okay. For ibuprofen, I think acetic acid is 4.73. I think ibuprofen is more like 4.5. But anyway, it's somewhere in the 4 to 5 range. And so just to keep in mind what this means, a strong acid typically has a pKa that's below 0, like H2SO4, HCl, HBr, HNO3. They all have negative pKas. Water, which is not a very strong acid, has a pKa of around 14, well, exactly 14. So this is much more acidic than water, but much less acidic than a strong acid. Esters are kind of similar to a carboxylic acid. There's a carbonyl group, there's an oxygen, but instead of being an OH, it's an O carbon. Okay, so it's like a carboxylic acid where you take the hydrogen off and put a carbon there instead. In fact, you can make carboxylic acids into esters by replacing the hydrogen with carbon groups. Esters are, again, super common in biology, in natural compounds. This is a whole series of compounds that are used naturally by, different plants to produce smells, odors, signaling, and these are often used to signal to insects that this is a great plant to come and pollinate. And many fruits and many foods that we eat, we can associate the flavor with sometimes a specific ester compound. So all of these esters, this first one that I have here, methyl salicylate, smells like wintergreen, smells like, mint. You can see the next one, 3-methyl butyl acetate, sometimes called amyl acetate as well. is banana smell. And so if you ever eat those banana candies, those artificial banana candies, that flavor, that smell, it's sort of banana-like, apparently is this. I read recently that the species of bananas that we eat right now are not the same species that we used to eat like 50 years ago. That species has like gone extinct or something. A virus wiped it out. And that those like banana candies taste a lot more like the ones from 50 years ago than the modern ones. So if you eat those banana candies and you're like, these don't really taste like bananas, that's because they taste like 50-year-old bananas, not modern bananas. So there's room there in the candy market for you to like invent a new banana flavor, I think. So that's the compound. Pentyl pentanoate, you can see there's an ester in the middle there. Apple, orange, pineapple, pear. Interestingly enough, if you have fruit punch, which is sort of sold as like a blend of a whole bunch of different fruits, no, it's a single ester. It's an ester that's not naturally found in fruits. It's a synthetic one that we make, but it doesn't taste like any specific fruit. It kind of tastes somewhere in the middle of a whole bunch of fruits. So they just call it fruit punch. It's almost like you blended a bunch of fruits together, but it's a single molecule, a single compound that they use to flavor it. Which makes me wonder, like, does that flavor of fruit punch, was there a fruit that's now extinct that like we evolved to detect? But now the fruit's gone and we still have the ability to smell it and we can remake the smell in the lab, but we can't find it in an actual plant that's still growing and alive. This makes me wonder. Anyway, esters. Amides. Amides, super, super, super common in biology, perhaps one of the most important functional groups in biology. Amides are the linkages between amino acids that make up proteins. So amino acids come together, they form these amide kinds of bonds. An amide bond is a carbonyl group bonded to a nitrogen. And that nitrogen can be NH2, that nitrogen can be NH, the carbon group, but it just needs the carbonyl with a nitrogen attached to it. This is a molecule of oxytocin. No one ever heard of oxytocin before? It's a small protein. This is sometimes called the love hormone. And if you pet a dog, it releases oxytocin in the dog's blood. So they love being petted, I guess. Not I guess, I know. Oxytocin has, it looks, this is like a medium-sized molecule. Remember we talked about big and small, and this one's medium-sized. It's got a lot of atoms. It's got a couple amides in here too. We should have a game, spot the amides. Well, here's one. I'll get us started. Carbonyl group with a nitrogen attached, right there. See any others? One right below it. Yeah, look right there. Another. One in pink here and here. What up here? There's one. There's one up there. One right there. What else? There's got to be another one. There's a nitrogen all on its own. Doesn't have a carbonyl group, so that's not one. Oh, there's one right here. There's an alcohol. Yep, that's it. Lots of amides in this molecule of oxytocin. Right? And so one of the things you guys are going to be asked to do in the future is I'll show you a molecular structure and ask you to pick out the different functional groups, circle them, identify them, and yeah. Amides, sometimes they're called peptide bonds as well. Well, they're called peptide bonds when they're part of a protein. If they're not part of a protein, they're just generally called amides. Nitriles is another one we're going to talk about. So it's nitrogen bonded to a carbon. No, a nitrogen bonded to a carbon could be a lot of things. It's a nitrogen bonded to a carbonyl. You need the carbon double bond oxygen and a nitrogen attached. Nitriles are anything that has a carbon triple bond nitrogen. Usually the carbon makes another bond, so it could be attached to some other R group, R just being the rest of the molecule that we're not concerned with at this moment. Carbon-nitrogen triple bonds are very strong. You've got to break 3 bonds to break that bond up. I'd say they're, I say here they're widespread. They're found occasionally, maybe is a more accurate way to say this. They're not super common, but they do pop up now and then. You can see in this molecule called crambene, this has got a carbon triple bond nitrogen right there. Crambene is anti-cancer agent. It's found in cruciferous vegetables. What are cruciferous vegetables? These are things like anything in the family with cauliflower and broccoli and Brussels sprouts, cabbage, all those sorts of things are the cruciferous vegetable family, and you can find crambene in there. Very polar, strong. If they're small, they're pretty soluble in water, like CH3CN. It's my favorite solvent, acetylnitrile. Just because it has all the properties that I look for my work as a photochemist. It's soluble in water. It's not very toxic. It's low boiling point, so it's easy to evaporate away. It doesn't absorb any light all the way down to the deep UV part of the spectrum. It's pretty cheap. It's got everything going for it. We'll talk more in this course eventually about choice of solvents, because up till now, like in first year chem, almost always the solvents that we use for doing chemistry is water. And organic chemistry, we probably rarely use water in organic chemistry. Well, we use a lot of it, but we use a lot of other solvents as well. And we'll talk about what some of those solvents are and when we might use them. But before we do that, we have a unit here on spectroscopic methods. And spectroscopic methods are basically like equipment, machines that you can use to do analysis on compounds to give you information about what they might be or how much you might have. So, I mean, I always think back to like 100, 120 years ago when organic chemists were trying to like figure out what reactions were happening, and they didn't have anything. They had no real good way. Let's say you have a little bowl and there's white powder in the bowl. What is it? Well, back then they had all these chemical tests, and they would heat it with tungsten dioxide and saw what color the smoke was. Like they had like this series of tests that they'd have to do to try to like narrow down what the structure was. Now we have spectroscopic methods, which gives us very quickly and directly information about the molecule. So the one we're going to be talking about is called infrared spectroscopy. We have around like 4 of these in our department, these spectrometers. Another important one is NMR spectroscopy, and we have one of those in the basement of Huggins. It's pretty big, takes up basically a room, just the instrument itself. It's kind of cool. It's got a superconducting magnet inside of it, bathed in liquid helium, because it's only superconducting at super low temperatures, and it creates a super strong magnetic field, and you put your sample in, and you can learn a tremendous amount. We're going to get to that one in chapter 4. But for now, we're going to talk about spectroscopic methods. We're going to talk about IR. And what spectroscopic actually means is measurements taken on compounds that involves light in some way. The light is somehow involved, typically absorbed or emitted by your sample, and then it's measured by the instrument, and you can learn something about it. So we have this electromagnetic spectrum picture here, and you can see it's broken up into a bunch of ranges. You've probably seen this same picture before. Right in the middle is what we would call visible light. Visible light has wavelengths in the range somewhere between about 400 and 800 nanometers. Outside of that range, we find these other different bands of light. So if it's longer wavelength than visible light, that means we are not able to see it. We get the infrared part of the spectrum. Okay. On the other side, shorter wavelengths, higher energy, we get ultraviolet light, which is here, and then we get X-rays, then we get gamma rays. Longer than infrared, we're into the radio, where microwave is a part of that, FM, AM, and so on. AM, FM is probably like not something people really, especially AM. I've never heard of an AM radio station in a long time. They should probably replace this with like 4G, 5G. These are probably more relevant to people's everyday life now. And I don't know where those are, but that's around where you'd find them. I wonder if 5G is, I don't know. I'm not going to make stuff up on the fly. So depending on the energy of light that is used, it causes different changes in the molecule that we can measure. X-rays, super high energy. They can be diffracted by nuclei, and it helps us determine the structure. It's called X-ray crystallography. Ultraviolet visible, so this is in the visible part of the spectrum, or just more energetic than that, causes what we call electronic transitions, which we're not worried about now. Infrared causes vibrational transitions. That's the one that we are going to be talking about. So when you have a molecule, any molecule that has bonds, right? So if you have a molecule with no bonds, like a noble gas, for example, IR can't be used to tell you anything about them. But if there's bonds, what's happening are these bonds are sort of constantly vibrating back and forth and back and forth. And you can see the picture I have down here of, I don't know what that is, HCl, we'll say. There's a small atom and a large atom, and they're vibrating back and forth. And that's just always going on, always. They're bouncing around, flying around in solution or in the gas phase, and they're also constantly vibrating. These vibrations happen with sort of specific frequencies, okay, or specific periods or frequencies. And what you can do is you can cause the compound to transition to a different frequency. I'm not going to get into the details of this. Quantum mechanics dictates that only specific frequencies are allowed for certain bonds, and you can go between those different allowed ones by absorbing or emitting energy. Whoa, these are super fast. They're not supposed to be going that fast, but actually, they're actually way faster than that in real life. But they're like super fast on here. Usually they go much slower. What's going on here is for molecules that has multiple different bonds, which is most of the case for organic molecules, what happens is these vibrations that are happening with these bonds aren't just, individual bonds vibrating. What happens is they all couple with each other, and you get sort of sets of vibrations where multiple bonds are sort of in sync with other bonds in the same molecule. And so an example here is this is just a CH2. Carbon, hydrogen, hydrogen. And those two CHs, those two bonds right here and here, those will vibrate back and forth, but they're coupled to each other, those CH2s. And there's two possibilities that we have. You can have what we call a symmetric stretch, which is the one on the left, where those two bonds come in and out in sync. They're extended out to their maximum length at the same time, and then they're compressed at the minimum at the same time as well. So that they kind of breathe in and out together. The other one is over here, and I don't know if you can notice the difference. They look kind of the same to me. But these are called an asymmetric stretch. So when one is stretching out, the other one is shrinking. So it kind of goes back and forth kind of like this. Okay? You think of my fists as being the atoms, the hydrogens. They're kind of going opposite each other. Right? So we have a symmetric and an asymmetric stretch. This would give you separate peaks, these would be different transitions for a different bond. You can now also have other ones for CH2s. You can have, this one's a scissoring, and maybe you can imagine why that's called scissoring, right? You can have a whole bunch of them here in a line, and you can see they're kind of rocking out there, which is, PowerPoint, come back to me. Well, that recovered quick. Where was I? Rock. So yeah, you can see why they're called rock. If you have a CH3, this is just another example of these. I mean, it's not important that you recognize the names of each of these kinds of transitions, just to know that there's a bunch of different possibilities depending on the group, and there's specific possibilities, and people spend a lot of time like calculating out what the possible ones and not possible modes are. I'm going to skip this, and this was meant to come up later, and I don't know why it's coming up now. So what we see then in infrared spectroscopy is we have an instrument, you take your sample, you put it in, you say scan, and what it does is it hits your sample with infrared light. Your sample will absorb a wavelength of infrared light if it possesses a functional group that vibrates at the same frequency as the light that you're giving it. If it doesn't have that functional group, there's nothing there to absorb, there's nothing that vibrates at that same frequency of light, then the light just goes straight through. So it looks like this. You have a spectrum, nice purple color here. And the way we do this is we start at a number, it's like around 4,000, and this is a frequency, okay? 4,000 centimeters to the -1. Frequency is inversely related to wavelength. So cm to the -1 is like an inverse centimeter. It's an inverse wavelength. So this is frequency. Sometimes it's also just called wave number. So you stick your compound in, the machine does a scan, spits out your printout, you look at your piece of paper, and it looks like this. It goes from 1400 typically to around 400. And there'll be, say, 3,000, 2,000, 1,000, all the way down to the end. And on the left-hand side, we have a measure which is called percent transmittance. Goes from 0 to 100. Transmittance is the percentage of the light that goes straight through your sample. So 100% transmittance means 0% was absorbed by your sample. So if you just put, helium in the instrument and ran a scan of helium, you would see something. Let's get a different color here. Let's go with blue. Helium would be a line like that, because there's no bonds. There's nothing in helium that can absorb, can vibrate. So just nothing really happens. But what you see for actual compounds, organic compounds, is you might see something that looks like, let's give you a different color, green. You might see something that looks like this. Okay, that's just a random thing that I drew, no specific molecule in mind. But you see these sort of peaks that are hanging from the ceiling. And what this means is the percent transmittance is less than half. So the majority of the light at that particular wavelength or that particular frequency is being absorbed by the molecule because of some vibrational transition. Some vibration that exists in the molecule has that frequency. And what we find is that specific functional groups always have very characteristic IR absorptions. So if you have an alcohol, alcohols always come over here. They always give you a peak that looks sort of the same. And what we're going to do is sort of march through our different functional groups and see where those show up. I just noticed, by the way, there's one functional group that I sometimes include that I didn't include this time, which is on my mind a little lately, is sulfides. Sulfides are functional groups that have a sulfur, either with a CH3, with a hydrogen, or just some other carbon group. Because sulfides are very strongly smelling, and they're what is inside skunk spray. When skunk spray you, it's sulfides. Because I almost got sprayed by a skunk last night. I was out walking, and I came close to a skunk. It went up on its 2 front feet, tail came out. I just ran the other way. I didn't get sprayed. I'm good. You'd know. This might have to be an online class too. Okay, so the infrared spectrum, I have it broken up here into 4 regions. Between about 4,000 and about 2,700 is where you find all of the bonds of hydrogen to something else. Whether it's an OH, an NH, or a CH or something, we find it somewhere in this region here. If it's a triple bond, carbon-carbon, which is alkyne, or this, what's that called? C triple bond N. Nitrile. Double bonds, carbon, nitrogen, oxygen are found there, and then single bonds between here and here. So we're going to look at some specific examples, and I'm going to show you guys when you see an infrared spectrum, how to analyze it, okay, and how to look for pertinent information that could be in there. Okay, here's an example of an alkane. This is octane. Okay, see the structure is right there. There's a grid here, which is maybe a little obnoxious. Hopefully you can see the, I'll outline it here for you to make it super obvious. There. So octane has a couple of features that are obvious. One is right there, right? Maybe here, I don't know, maybe there as well. First of all, what we're going to do when you see a spectrum like this is I want you, like, first thing you think of is go to 1600. Okay, see 1600 right there, and draw a vertical line. Yeah, I'm going to just draw the vertical line right up there. Then go to 3000 and do the same thing. 3000 is here. We're going to draw a line up here. All right. So that 3000 line, remember I said this is the region where you find bonds to hydrogen. And hydrogens are like everywhere. If you have an sp3 carbon bound to hydrogen, they show up just to the right of 3000 reciprocal centimeters to the -1. So that's this right here. They don't go past 3000. And that's why I got you to draw a line at 3000. There should be nothing on the other side of 3000 from sp3CHs. They all show up on the right of that line. What's sp3 mean? Told you this is going to be important, didn't I? sp3 means all of the bonds are single bonds to that carbon. No double bonds, no triple bonds. This other line at 1600, this whole region that you see right here is where you find single bonds. Now, every organic molecule has single bonds. They all kind of show up all over the place in there. There's not very many characteristic peaks that show up 1600 and beyond. So we often call this region the fingerprint region, which means, like, think about when you go get your fingerprint taken. Let's say you go into a police station, they take your prints are on file. What are your prints, what does your fingerprint tell them about you? What information does it give you? No, there's no DNA there. It's just your fingerprint. They actually can't tell anything from it. They can match it to, if they get your fingerprint somewhere else, they can match and say if they're the same or different. But you can't just look at a fingerprint and say, oh, this is a 48-year-old Caucasian male. Like, you can't get that kind of information from a fingerprint. All you can do is use it to positively identify something, if you already have a copy of the fingerprint. So that's the same thing in these infrared spectra. The fingerprint region, there's not really useful information in there for us to say, oh, this is the structure or that's the structure, at least not the level that we're looking at in this course. But if somebody had made a compound and ran the spectrum and published it, you could make the same compound and publish it and match those parts up. And if they match, then you've made the same compound as the other person. So it's like identifying like that, but it's not useful for saying what's in the molecule. Whereas this one over here, we can say, oh, there's sp3CHs, which maybe is not super rare in organic chemistry, but there's nothing else on this molecule. Other than that, the rest of the spectrum is very clean, except for the fact that I drew all over it. Alkenes, one octene is a little bit different. Okay, there's a little thing here. Little bond there. I shouldn't have just done that. You guys can see that clear. Now I can't erase it. So I missed this one here. I'm going to stop doing this, by the way. I'm not going to trace them anymore. This looks similar before. So we're going to go to 1600, and draw a vertical line. Everything over here is fingerprint, which we don't really concern ourselves with. We draw another line at 3000, which is over here. Good thick line. Now we have stuff going on the left of that line and the right of that line. What's on the right of the line? Yeah, sp3 CHs. So by seeing that peak, we know that that compound that we put in the instrument has carbons with hydrogens on them, and those carbons are sp3 hybridized. Okay, and look at the molecule. We have a whole bunch of them on the molecule. Now, there's this one over here. What do you think that is? sp2. sp2 CH bond here somewhere. And right there. We have two sp2 carbons. There's 3 hydrogens on sp2 carbons. Right over here. Right over here in the structure. And therefore, we see these peaks show up in the infrared spectrum. Fantastic. Okay, so we can see the difference now between sp3 and sp2 CHs by cutting them in half at the 3000 wave number mark. Also, there's this new peak over here, somewhere in the 1620, 1680 range, which is where we find double bonds. We see a little blip right there. Like little tiny peaks like that, we don't concern ourselves with. We're looking for strong features that typically, you know, go a quarter at least of the way down. So we see carbon-carbon double bond, we see fingerprint region, we see the sp3 and the sp2 CHs. So here's comparing these two spectra back to back. And what you can see, these lines at 1600 and 3000 are drawn in. You can see there's this double bond here in this example, but not up here. And you can also see there's no sp2 CHs here, but there is here. So you can distinguish an alkene from an alkyne using infrared spectroscopy. Why are you in the middle of nowhere? Okay, lycopene. This is a molecule. It's found in, it's the red color of tomatoes. I have a whole thing on lycopenes later on, which is why I stuck this in here. But this is an actual spectrum of this compound. You can see that very weak CC stretch. There's sp2, sp3, CHs. Anyway, alkynes. Next one, carbon-carbon triple bond. Carbon-carbon triple bonds are really easy to pick out because that triple bond part of the spectrum, which is, I don't know, like 2700 to 2000, say. This is 2000 to about 2700. There's really nothing else that comes here besides triple bonds. There's actually this one, which is carbon dioxide, which you can eliminate if you run your spectrum correctly. But they didn't. They see a little CO2. But this is your carbon-carbon triple bond right there. Now, we didn't do our first thing. First thing, right, we're going to draw a vertical line at 1600 and a vertical line at 3000. So this is saying, what do we have here? It's sp3, CHs. What about right there? It's nothing. That's where we'd find sp2. We don't have many sp2 atoms in this molecule. What are the hybridizations of these carbons in the molecule? They're both sp. So this big, strong peak there, SPCH. So it's a little bit left again, in this case around 3,300 wave numbers. See, it's a bit out a bit from where the sp2s are, very strong. Now, alkynes don't always have CHs. This one does because it's on the end. If it's on the end of a chain, we say it's a terminal alkyne. Terminal means it's at the end. If it's not, we call it an internal alkyne. So internals don't have SPCHs, so you just see nothing up there. But if you see it, that's a good sign that you have an alkyne. Other than that, there's no double bonds. There's a bunch of fingerprint stuff to the right that we're not going to be concerned with. So now we can tell apart alkanes, alkenes, and alkynes by running an infrared spectrum, which is great. So if we're doing a reaction where we start with an alkane and we're trying to make an alkene out of it, we could then just go test, put it in the spectrometer. I see Jeff. Dr. Banks, I should say. Aromatics. Aromatics maybe aren't too surprising here. We have 1,600 as our vertical line. 3,000 cuts all this mess sort of in half. This compound, ethylbenzene, has CH bonds that are both sp3, and all these carbons are sp2. So we see sp2 CH stretch. The stretch just means that's the type of vibration. And you can see these, which are sp3 CH stretch. So they're both present in this molecule. But notice we don't have any double bonds in here. No alkene. Why not? This has 3 double bonds in the structure, doesn't it? Kind of, but not really. People are like, what do you mean? I'm looking at the structure. I see 3 double bonds in there. Well, in this case, it's benzene. It's technically not really a double bond because this has a resonance structure where you can pop these electrons around to make this. So the true structure is a 50-50 blend of those 2 structures, which means I'm going to draw it over here on the left. We sometimes draw it like this, or sometimes you see benzene drawn with a circle in the middle. That means on average, each of those carbon-carbon bonds are 1.5. There are no real double bonds in benzene because of this resonance structure. So the infrared knows that. We might look at that structure and be tricked by the way we drew it because we're limited in how we draw structures based on the rules of Lewis structures. But the infrared spectrometer is smarter. It looks at it and says, that compound has no double bonds. There's nothing in this part of the infrared spectrum. And we think about it and like, oh yeah, I guess it doesn't really have double bonds in the way we think of double bonds. It has 1.5 bonds, which we can't really draw using Lewis structures unless we draw resonance structures like what we see here. Okay, so the rest of what we see here is fingerprint, nothing else really of interest here. And there's some fine details, like you can see this little pattern of 4 mini peaks. Those are characteristic of a monosubstituted benzene ring, meaning there's one thing on the ring. We're not going to get into that level of detail. There's no carbon-carbon double bonds. That's what's important in this example. It's 9:20. I'm going to go for 1 more minute. This example is ethers. Ethers, remember, have an example would be CH2, CH3, CH2O, CH3. It's got an oxygen with carbons on either side. We're going to draw a vertical line at 3000, and you're going to see a whole bunch of sp3 CH stretches. That means the carbon, hydrogen are stretching like that, back and forth, vibration. No double bonds. So if you go to 1600, this is all kind of blank, no double, no triple. But what we do see for ethers, this is going to be one of the rare times that we're going to dive in to the fingerprint part of the region. We think there's an ether there. We should go look in there as well. And what you see somewhere between about 1050 and 1150 is a quite strong peak. You know, it's certainly this guy, this peak sort of emerges larger than all of the other peaks that you can see in that part of the spectrum. Okay, and the strength or the size of these peaks has to do with, in a complicated way, has to do with the electronegativity difference between the atoms. So when you have atoms that are very electronegative bound to carbon, they typically give you strong peaks. So a carbon double bond oxygen is typically much stronger than a carbon double bonded to carbon, as an example. I'm going to pick back up on the ethers slide when we come back next week. So I'm not going to go any further than that now, but I do have office hours starting in 10 minutes. I'm going to just unpack here, go down to my office, and get into our team site. If you don't know how to do office hours, by the way, there should be a Teams team on your Teams called Chem2513A1B1 office hours. So those are shared between the two sections. I always just jump on that, and you can just jump on anytime, and we can chat. Awesome.
Thank you.
No problem. See you guys. Goodbye, everybody.